Hello everyone, welcome to this lecture. In the previous lectures, we have studied vibration and model analysis of single and multi-degree of freedom systems. We also studied the concept of frequency response function, which characterizes a system in the frequency domain. In this lecture today, we are going to talk about impulse response function, which basically characterizes a system in the time domain. We will also talk about how to find response of a system to a given transient force or a set of forces using impulse response function. So, today's topic is impulse response function and response to transient forces. So, a brief outline of the lecture is as follows. First, we will define what is unit impulse, then we will determine the impulse response function of a single degree of freedom system with viscous damping. Then we will see the concept of convolutional integral, which basically is about determining the response of a system to transient force using impulse response function in the time domain. Then we will look at multi-degree of freedom systems with proportional viscous damping and try to find out the response to transient forces of this system. We will define impulse response function matrix. Then we will extend our discussion to multi-degree of freedom systems with non-proportional viscous damping, and then we determine the response to transient forces and determine the impulse response function matrix for this system. We will at the end also look at the response model in the time domain. So, let us first of all define what is called as unit impulse. So, impulse basically is, if we consider a force acting for a short duration, then impulse is a product of the force into the time duration, assuming the force is constant over the time over which it is acting. Okay. So, let us say that we have a force, let us say acting over a time duration delta t, and let the magnitude of the force is f naught, right. So, the impulse is basically force into time duration. So, if I choose the force and time duration such that the impulse is unity, then it is basically referred as unit impulse. However, now we are going to define a unit impulse which is ideal, okay, and which basically is referred as direct delta function. Such a definition can be derived from this pulse we have just shown here. If we increase the height of the force or the magnitude of the force and decrease the duration of the force, keeping the strength of the impulse constant, then in the limit what is going to happen? When delta t tends to a very small number, infinitesimally small quantity, then the height f naught will tend to infinitely large value in order to ensure that the strength of the impulse is unity. So, if we try to show this process through a figure, so let us say if we increase the height or magnitude of the force and reduce the duration of the force, okay, and we take the limit of this. So, this is nothing but the force is a function of time. So, if you take limit of this force, then in the limit what is going to happen? This force will be concentrated at the origin, right, like this. Force would be concentrated at the origin when delta t or the duration of the force tends to infinitesimally small number, right. So, this basically is called as direct delta function, del, represented by del. So, delta of t is basically called as direct delta function, right, and it is defined such that delta of t is not equal to 0 at t is equal to 0 and it is equal to 0 at t not equal to 0, and its integration over the time axis is unity. So, which basically forces the impulse to have a unit strength. So, this is basically the definition of direct delta function or a unit direct delta function, which basically is an idealized unit impulse. So, here delta t has units of force and its integration over time axis is unity, which basically means that this force amounts to producing a unit impulse on the system. So, let us now determine the response impulse response function. Impulse response function, which we will abbreviate as IRF, for a single degree of freedom system with viscous damping. So, let us take a single degree of freedom system with viscous damping in this manner, and let us say it is subjected to a unit impulse. It is subjected to a force delta of t, and because as we saw the delta of t basically is equivalent to applying a unit impulse on the system. And let us determine what is the response x. The equation of motion for this system we already have derived in the previous classes as C mx double dot plus Cx dot plus Kx is equal to force. In this case the force is delta of t, and we are also assuming that before the delta of t is applied, in 0 initial conditions exist, right. The conditions are 0 before application of impulse. So, after impulse is applied, it is basically going to change the momentum of the system, because we know that by Newton's law the force acting is rate of change of momentum. So, if m is the mass, u is the velocity, rate of change of momentum is dmu by dt, and that is nothing but equal to the force acting on the system. And this also therefore can be written as f dt is equal to dmu, right. So, this basically says that the f dt, which is nothing but the impulse acting on the system, will amount to change in momentum. Therefore, in the present case the momentum can be written as change in momentum can be written as mass, if let us say u is the final velocity after the application of impulse, and if initial velocity is 0, then that is the change of momentum, and what is the strength of the impulse, that is unity. So, we can simply say unity, right, and therefore, this gives us u is equal to 1 by m. So, this means that once the impulse has been applied, then if that time is designated as t is equal to 0, then at t is equal to 0 the displacement is 0 and the velocity, that is x dot, is equal to u, which is basically 1 by m, right. So, this basically gives us the conditions on the mass m just after the impulse impulse has been applied, right. So, we have found out earlier the response of a single degree of freedom system with viscous damping subjected to when some initial disturbance in the form of initial conditions act on the system, and now we can apply these initial conditions to find the response. Let us write down the response of the system would be x of t is equal to e to the power minus zeta omega and t into a cos omega n 1 minus zeta square t plus b sine omega n under root of 1 minus zeta square t. So, if you impose the first initial condition, the displacement is 0 at t is equal to 0, then we basically get 1 here, then a 1 plus b into 0, right. So, this basically leads to the the value of the first arbitrary constant, which is a, that is 0, right. So, there are two arbitrary constants a and b, and we are determining those constants using the these two initial conditions. So, the first constant turns out to be a is equal to 0. Now, the second constant, let us determine the velocity. So, we need to differentiate this x of t. So, and after, of course, we can substitute a is equal to 0 here. So, the first term disappears, and then we apply the formula of product of differentiation of product of two functions. So, that gives us zeta omega n e to the power minus zeta omega n t into b sine omega n under root of 1 minus zeta square t, right, plus e to the power minus zeta omega n t, differentiation of sine would be cos omega n under root of 1 minus zeta square t into omega n under root of 1 minus zeta square, right. So, let us apply the condition on velocity. So, x dot t at t is equal to 0 is 1 by m. This would be 0 at t is equal to 0 plus at t is equal to 0, this is 1 into b into 1 into omega n under root of 1 minus zeta square, right. So, this leads to the constant b equal to 1 upon m omega n under root of 1 minus zeta square. That is the value of the second arbitrary constant. So, let us substitute these two constants in the expression for x of t, right, and that expression would be e to the power minus zeta omega n t. A is 0. So, the first term goes away, and the second term is b, whose value is m omega n under root of 1 minus zeta square in the denominator, and then we have into sine omega n under root of 1 minus zeta square t. So, this is the equation we are getting. And now, what is this? This is nothing but the response to a unit impulse, right. This expression is nothing but response to a unit impulse acting on the system. And this is nothing but impulse response function, right. So, this is IRF, because IRF is defined for response of the system to a unit impulse. This is similar to the definition of frequency response function. The frequency response function we defined as response of the system to a unit amplitude harmonic force at frequency omega, right. So, similarly in the time domain we define the the force as a unit impulse force, and then response of the system to this unit impulse force is nothing but the impulse response function. So, impulse response function is generally denoted by h of t, right. So, therefore, we write h of t is equal to minus zeta omega n t upon m omega n under root of 1 minus zeta square into sine omega n under root of 1 minus zeta square into t. So, this is the IRF of the single lever of freedom system with viscous damping. So, if you sketch this IRF, then it looks something like this. So, like this. So, it starts from 0, because displacement is 0, and then it has certain initial velocity, and then the response decays exponentially with time. So, this is nothing but h of t. So, if we have an undamped system, if the system is undamped, then in that case zeta is equal to 0, right, and therefore, in that case h of t would be simply 1 upon m omega n sin omega n t. That will be the impulse response function for a undamped system. So, for an undamped system, the amplitude of the response does not decay and stays constant. Something like this, right. The other thing I should mention here is that when we derive the impulse response function for a single degree of freedom system with viscous damping, we have also assumed that system is under damped. Okay. So, that was the assumption, because when we wrote the equation for the free vibration of the system with given initial conditions, that expression was basically corresponding to an under damped system, right. So, this is for under damped system, and in practice often the damping is low and then the systems are under damped, right, and hence this is something will be quite applicable for systems in practice. So, in this manner we have found the impulse response function. Now, let us say that a transient force acts on the system, then how can we find response of this system? Okay. So, response of a single degree of freedom system with viscous damping to a transient force. So, let us write down the equation mx double dot plus cx dot plus kx, and now the force here is f of t, and this force is something like this. So, it is a transient force, and let us suppose the force goes like this, right. So, it is a kind of a a force for a finite duration. So, a transient force is a force which acts for a finite length of time on the system, right. So, how can we find the response of the system to such a force? So, our objective is to find what is x of t. So, now here, and that we are going to determine in the time domain. Okay. So, now here we make use of the impulse response function we got earlier, right, and then try to determine the response of the system to this force. So, for this purpose, let us divide this force or represent this force as a series of constant magnitude force steps, a series of force steps, right. We can approximate this transient force as. So, let us say this is the approximation. So, through a series of these discrete force steps, we are trying to approximate the force, correct, and let us now consider the response due to one of such steps, right. So, let us say there is a force step at location tau, and let the width of the force step is del tau, which is constant for all the force steps, and let us now determine what is the response of this force step. So, we are basically looking at this fourth step now. Right. So, it is at a location tau seconds and it is of width delta tau. So, now this fourth step can be approximated as a pulse, as an impulse of strength f tau. So, height of the force here is f tau, right. So, that is the impulse strength of this pulse, and then we would like to determine what is the response at location tau, at location t, right. At location t, what is the response? So, this is the location t. So, what response this impulse creates at location t? So, earlier we looked at the definition of delta of t, right. So, the delta of t was a impulse, right, where the force is concentrated at the origin. So, this was delta of t. So, this impulse, if it is translated on the time axis, right, let us say to a location tau. So, therefore, we have this impulse which is now acting at this location, right, at location tau. Then this impulse is basically referred as delta t minus tau. So, delta t minus tau is an impulse acting at location t is equal to tau. Okay. So, this is impulse acting at location t is equal to tau, and that is represented by delta t minus tau. So, similarly, if I look at the response, then the response which is created, right. So, h of t was the impulse response due to delta of t, we showed that this is going to be something like this, right. So, when the impulse acts at location t minus at t is equal to tau, the impulse response would also start only at that time. So, it will also start here at delta t at t is equal to tau, and this is therefore designated as h t minus tau, right. That is the impulse response starting at t is equal to tau. So, in our case now, the force pulse is acting at tau location at time t is equal to tau, and the strength of the that impulse is f tau into delta tau, right. And we already know if a unit impulse acts at t is equal to tau, its impulse is the response created is h t minus tau. So, but if the impulse is of strength f tau into delta tau, the impulse is the response due to this can be obtained by product of the strength of the impulse and the impulse response due to unit impulse. So, that is basically the idea behind finding the response due to this particular force step. So, let us do that on the next page, and therefore, we can write down delta of x. So, that is nothing but we are representing it as the response due to force step whose width is delta tau, and that should be equal to the strength of the force pulse, which is f tau into delta tau, multiplied by the impulse response h t minus tau, right. And h t minus tau is taken because the force step is acting at t is equal to tau. So, this is nothing but the response due to that force step. So, if we want to know the total response, we need to then simply add the responses due to all such 4 steps. So, we say that x of t is equal to f tau delta tau h t minus tau, right. So, all 4 steps the response due to all such 4 steps has to be added. So, tau for all those steps would be different, right. So, therefore, the responses that are created by different 4 steps, they would be at different instants of time, right. and all such responses are to be then linearly superimposed, right, in order to get the total response. So now if we want to find the response due to the actual transient force acting, then the width of these force steps should be reduced. Now we take limit delta tau tending to 0, okay, because that would give a very close approximation of the transient force. This summation sign will become a sign of integration, right, because delta tau is now becoming an infinitesimally small width, right, and that requires infinite number of such force steps to approximate the transient force. And therefore, no longer we have the finite number of steps, but we have now the infinite number of steps. So, we get x of t is equal to integration from 0 to t f of tau and h t minus tau, and now the force step delta tau becomes infinitesimally small. So, we represent it by d tau, right, and the integration limits are from 0 to t, the time till which we want to find a response. So now this basically is nothing but the response of the system to force f of t, right. So, this gives us the response to transient force. And this is in the form of an integral, and it is called convolution integral. So, here in the frequency domain earlier we saw that the response of the system can be obtained by multiplying the input force in the frequency domain with the frequency response function magnitude and phase at that frequency, right. And therefore, the process was simply you multiply the output, you multiply the input with the system characteristics and you get the output. But in the time domain, it is not simply multiplication, it is a process of convolution, right, and this operation is generally indicated by a star operator like this f of t. So, this is the symbolic representation of convolution of input force with the impulse response function of the system, right. So, this represents convolution. Okay. So, in the time domain, the input and system characteristics, which is the impulse response function, has to be convolved in order to find the output. So, let us now consider a multi-degree of freedom system with proportional viscous damping. Okay. And let us find out the response to transient forces. And then we are going to use a modal analysis approach. Okay. We are going to use a modal analysis approach to do that. So, the equation of motion for this system can be written as mx double dot plus cx dot plus kx is equal to, now we have a vector of transient forces. Here C is now proportional to a linear combination of stiffness and mass matrix. So, now we can use the eigenvectors of the corresponding undamped model, right, in order to diagonalize these equations of motion, right. So, we first consider the modal transformation in terms of the eigenvectors, which are the mass normalized eigenvectors, right, and y is the vector of model responses. And then we also pre-multiply, after substituting this x, we pre-multiply by eigenvector matrix transpose, and then we use orthogonality properties, right, of the eigenvectors. Okay. So, that basically gives us, of course, we first then do that phi transpose m phi y transpose plus phi transpose c phi x dot y dot plus phi transpose k phi y is equal to phi transpose f of t, right. And then in the light of orthogonality properties, this matrix will be a unity matrix, phi transpose m phi. Phi transpose c phi can be written as a diagonal matrix of 2 zeta r omega r plus phi transpose k phi is matrix of diagonal matrix of omega r square. So, this all we have studied in the previous lectures. Y is equal to, now this will be a vector of modal forces, right. Let us call it Fr. This is a vector of modal forces, right. So, these are now all the decoupled equations, and then now we can consider say Rth model equation, right. Let us go to next page. So, if I consider the Rth model equation, that is nothing but y r double dot plus 2 zeta r omega r y r dot plus omega r square y r is equal to f r t, right. So, that is the Rth model equation. So, here now we can use the impulse response function of the single degree of freedom system we got, right, to find out the impulse response in the Rth mode, and therefore, we can write this as HRT t to 0 sorry YRT is equal to integration 0 to t f r tau. Now, HR tau we will have here the mass m for the model mass for the Rth mode here is 1. So, m is 1, and then we have omega r, that is the natural frequency of Rth mode, into 1 minus zeta r square, right, into sine omega r under root 1 minus zeta r square, right, and then we have t minus tau, right, into d tau, right, and also I have also e to the power minus zeta r omega r t minus tau, that term is also there in the numerator. So, this becomes now the modal response. So, now we can we also have the Fr, right. So, Fr is basically the dot product of the Rth eigenvector, right, with the vector of transient forces. So, this is Fr t, right, and now this also we can substitute in the expression for Yr, and then we can find the physical response in physical space, right, response in physical space we can find as x of t, right, is equal to summation of phi r t into y r t. phi r transpose into y r t, with r varying from 1 to the number of modes of the system n, is not it. So, now we can substitute y r t here and also substitute f r t, that modal force, and noting that the eigenvectors they are constants, they are not, they can be taken outside the sign of integration. So, we can write this as summation r is equal to 1 to n, then we have so I think here we will not have transpose, this transpose is not required. So, we will have phi r, right, phi r into integration of 0 to t, then we have e to the power minus zeta r omega r t minus tau upon omega r into 1 minus zeta r square sin omega r under root 1 minus zeta r square t minus tau, right, into f r. So, f r is phi r transpose f of t, right. So, of course, here we will have f of tau. Into d tau. So, this is nothing but the response to transient forces. So, we can see here, if I know the force, if I have been given the forces that are acting on the system, right, in the form of the force vector f tau, then I can substitute that here and then perform this integration, and that would basically give me the response to transient forces. So, this is response to transient forces. Let us now define impulse response function IRF for multi degree of freedom system with proportional viscous damping, the system just now we analyzed. Right. So, for that you see we have n number of n degrees of freedom. So, the forces can be applied at any of these n degrees of freedom, and the response can be measured at any of these n degrees of freedom. So, therefore, there are n square number of IRFs that can be defined, right. I can choose, let us say the response at jth degree of freedom, and if the unit impulse is applied at kth degree of freedom. So, this is nothing but the impulse response function, right. So, this impulse response is nothing but the response at jth degree of freedom when unit impulse is applied at kth degree of freedom and no forces at rest of the degrees of freedom. So, that condition also has to be ensured. So, we have to apply impulse only at kth degree of freedom, and we need to apply unit impulse and then measure the response or find the response at jth degree of freedom. That is nothing but the impulse response function HJKT. So, if there are n degrees of freedom, we have n square FRF, and this we can form a matrix of impulse response function. So, this we can call as the IRF matrix, and this can be then written as H11, H12 going up to H1n, then H21, H22 going up to H2n, and then we have Hn1, Hn2 going up to Hnn, right. And of course, this matrix will be symmetric because of the principle of reciprocity. So, let us now determine HJK, what is the impulse response function of the multi-degree of freedom system with proportional viscous damping, right. Let us try to determine what is HJKT, right. Let us write the expression we got for the response due to transient forces, right, and that expression is R varying from 1 to n summation, and then we have phi R, okay, and then we have integration from 0 to t e to the power minus zeta r omega r t minus tau upon omega r under root of 1 minus zeta r square sine omega r under root of 1 minus zeta r square t minus tau, right, and then we have phi r transpose f tau, right, that is nothing but and d tau. So, that is nothing but expression we got for the response to transient forces. Now, in our case to find JKT, we can define the force vectors f tau as forces of all zeros except the force at kth degree of freedom being applied like a delta function, so that it results into a unit impulse, right. So, this is kth df. So, when this is done, what is going to happen? The phi r transpose f tau, this product would basically be equal to phi k r, that is all, the kth element of the eigenvector, that is phi k r multiplied by delta of tau, right. So, of course, here also I need to write delta tau because we are defining f of tau. So, this is the product. So, now if we substitute this here and we also note another important property of direct delta function, that is called shifting property, which says that if I have any function, right, let us say if I have a function g of t, right, and if we look at this integral t minus t, right, into dt from 0 to tau, right, say minus infinity to plus infinity, we can do that, okay. So, when this integral is taken, then this basically gives the value of g at t is equal to capital T. So, this integral basically picks the value of the function g at the location where the delta function is acting, that is t is equal to capital T. So, if we use this property in the expression we have, then the result would be r is equal to 1 to n phi r, okay. So, now in our case the delta function is acting at tau is equal to 0, right, because delta tau means the delta function at tau is equal to 0. So, therefore, the integral basically would pick the value of the coefficient term at tau is equal to 0. So, this expression after integration would be simply minus zeta r omega r t upon omega r under root 1 minus zeta r square into sine omega r under root of 1 minus zeta r square into phi k r, right. So, this is nothing but the response we are getting when a unit impulse act at the kth degree of freedom, right, and therefore, response at all the degrees of freedom basically would correspond to the impulse responses corresponding to kth degree of freedom, and hence this is also equal to the kth column, right, kth column of the impulse response function matrix. So, this is nothing but the kth column of the impulse response function matrix. And if I want to know hjk, then I just need to take the jth element of this column, right, kth column, just we need to take the jth column, and therefore we can write down here the hjk t as so r varying from 1 to n, and then I have simply the phi jth element of this eigenvector I need to take phi j r, right, into phi k r into e to the power minus zeta r omega r t divided by omega r into 1 minus zeta r square multiplied by sine omega r under root of 1 minus zeta r square. Okay. So, this is nothing but now the impulse response function hjk. Okay. And we see that on the right hand side we have all the modal quantities, right, phi j r, phi k r, okay, and then zeta r, omega r, these are all the properties of the rth mode, and then this summation runs from r is equal to 1 to n. So, each term on the right hand side gives the contribution of a particular mode to the impulse response function. So, this expression is similar to the expression we got for the FRF earlier, right, in the previous lecture, that it consists of a sum of modal contributions from mode 1 to mode n. Let us now take a multi-degree of freedom system with non-proportional viscous damping. So, for this system the damping matrix cannot be considered as linear combination of mass and stiffness matrix, it is not proportional, and therefore, as we discussed earlier, we will consider the equations of motion in state space. Therefore, the equations of motion in state space are A z dot plus B is equal to F bar T. So, this equation we derived when we considered modal analysis of multi-degree of freedom systems with non-proportional viscous damping, and here the vector F bar tau is nothing but consists of vector F tau Ft, which is the vector of transient forces acting on the system, and a vector of zeros, right. So, this is a 2n by 1 vector, right, and F of t is nothing but a vector of n forces acting at n degree of freedom. This is also a vector of n by 1. So, again we follow a modal analysis approach to find the response, right, and our objective is to find a response, the response to transient forces. That is what we want to find out. So, therefore, we now consider the modal transformation Z is equal to the eigenvector matrix phi bar of the system in state space and the vector of modal responses in state space, right, and then we pre-multiply by phi bar transpose, which is the normalized vectors in the state space, normalized eigenvector matrix in the state space, and then use the orthogonality properties. Of these eigenvectors. So, what we are going to get? We would get phi bar transpose A phi bar y bar dot plus phi bar transpose B phi bar y bar is equal to phi bar transpose f bar t, right. And based on the authoritative properties, this phi bar transpose A phi bar will be a unity matrix, y bar dot plus phi bar transpose B phi bar, right. It will be a matrix of eigenvalues. It will be basically minus, it is matrix of eigenvalues S bar R, right, into y bar is equal to, this will be a vector of modal forces, right. So, which we can write as F R bar T, okay. So, let us now consider, so these are now 2n number of first order equations, they are all decoupled equations. Let us consider rth modal equation. If I consider rth modal equation, then what do we get? We get y bar dot, right, r minus s r bar, right, and y r bar is equal to f r bar, correct. So, that is nothing but the rth modal equation. And now the question is, can we use convolution integral here to find the response? Then the answer is yes, we can find out, because it is a system subjected to a force Fr. So, if I know the impulse response for this equation, then I can find the modal response. So, let us write that. So, the by convolution integral we can write down y r bar is equal to integration of from 0 to t, right, and then I have the modal force F r bar tau. Then I need impulse response in the rth, for rth modal equation. Let us represent it by h r bar into t minus tau into d tau, correct. So, this is nothing but the rth modal response, okay, based on convolution integral. So, that is perfectly fine. But now the question is, what is h r bar t minus tau, right. So, it is nothing but the impulse response okay, impulse response for rth mode, right, it is an rth complex mode. So, what is the impulse response for this? Now, for the previous case where we discussed the proportional damping, the equation was corresponding to a hypothetical single degree of freedom system, and then we can therefore use the impulse response function we derived for the single degree of freedom system. But in this case, we would like to first find the impulse response of the system, right. It is a case of non-proportional damping, and therefore, let us determine the impulse response first. So, let us find out the impulse response first. So, let us find out h r t minus h r bar t minus tau, right. So, to find impulse response for rth mode, we take the rth modal force as a force given by delta function. So, it will result into a unit impulse in the modal domain, right, and therefore, the equation would be y r dot minus S R y r bar is equal to delta of t. And now we take Laplace transform of both sides. So, Laplace transform of y r bar dot is S times y r bar, right, and then we are assuming 0 initial condition on y r bar, and hence that the second term is 0, and then we have minus S r bar y r bar is equal to the Laplace transform of the direct delta function is unity. So, therefore, from here what do I get? y r bar. So, that is nothing but the it is in the Laplace domain. So, y r bar s is equal to 1 upon s minus s r bar. So, I get a now expression in terms of s, right, and then we can take the inverse Laplace transform of this. So, taking inverse Laplace transform, we get y r bar t is equal to e to the power s r bar t, right. So, that is the inverse Laplace transform of 1 upon s minus s r bar, that is e to the power s r bar t. So, this is nothing but the response when delta of t is applied in the model domain, and therefore, this is nothing but the impulse response function h r bar t, right. This is the impulse response IRF for rth mode. Okay, it is the impulse response function for rth mode for a multi-degree of freedom system with non-proportional viscous damping. Now, we can substitute this HR bar t in the equation for YR bar, right. So, let us do that. So, let us write that on the next page. So, we get YR bar t is equal to integration, right. So, first we have the term, let me write that again here, f r bar tau h r bar t minus tau into d tau. So, this was the expression, and now we substitute in place of h r bar t minus tau the impulse response we just got, and that is nothing but e to the power s r bar t minus tau into d tau, right. And now we can substitute f r bar here, and so because we know that f r bar tau is nothing but the dot product of the rth eigenvector, that is phi bar transpose times f bar tau, that is nothing but the f r bar, and therefore, the response in physical space we can obtain as y r sorry, I want to use the model equation. So, I have now z, right, is equal to summation from phi bar r into y r bar, right. That is nothing but the modal transformation with r varying from 1 to 2n. There are 2n number of modes, right, and therefore, I can write this as phi bar r. Now, in place of y r bar, I can write down integration from 0 to t. So, then I have e to the power s r bar t minus tau into phi bar r transpose f bar tau into d tau. So, that is nothing but the response in physical space to the transient forces. So, using this we can find the response in physical space. We need to just introduce here the vector of transient forces acting and then perform this integration. Let us define now the impulse response function for this system, right, and that we would like to find out what is h j k, right. This we would like to find out the response at j degree of freedom if the force is acting at the k degree of freedom. So, we again use the expression we got previously, and we basically define the force vector now, right. So, the force vector f bar t is nothing but f of t and vector of zeros here. So, here we apply unit impulse at k degree of freedom and no force at rest of the degrees of freedom. So, hence f of t is given by this. And now we write down the response, right, which is r is equal to 1 to 2n phi bar r, right, integration. So, we had e to the power s r bar t minus tau into then phi bar r transpose f bar tau into d tau. So, this is the expression we got for the responses due to transient forces. And now, if we substitute f bar tau here, okay, and also represent. So, we should also recall that this phi bar r can be written as phi r into s r bar, like this. That is what we can write down. We can divide it into displacement coordinates and velocity coordinates, and displacement coordinates are phi r and the velocity coordinates are of the eigenvector are phi r into this r. Right. So, if we substitute this, we get r is equal to 1 to 2n. So, here I am going to write down phi r s r phi r, right, sorry, this r is outside, r, and then I have 0 to t e to the power s r t minus tau into phi r s r phi r transpose, here I have f of tau and 0 with d tau, right, something like this. So, now if you also represent the z by the coordinates x of t and x dot of t, that is the displacement coordinate and velocity coordinate. So, the displacement part of the response can be given by r is equal to 1 to 2n phi r transpose integration e to the power s r bar t minus tau into f tau into d tau. So, now if you substitute in place of f of tau the vector f of t, and then obtain the response, then that would be nothing but the impulse response, and that can be then written as h j k t is equal to summation of phi j r phi k r e to the power s r t, right, and with r varying from 1 to 2n. So, to arrive at this, we have made use of the shifting property, right, and then after finding the the responses, displacement responses, which basically is nothing but the kth column of the impulse response function matrix, we just take the jth element in that vector, that basically gives us h j k t. So, now we can also define the response model. In the time domain. So, if there are forces acting at all degrees of freedom, and if I am interested to know the response is, let us say at let us say ith degree of freedom, right, then I can determine that response using the impulse responses, right, at corresponding to different degrees of freedom. Okay. So, I can do a convolution between Hi1 into the transient force which is acting at the first degree of freedom plus the response at ith degree of freedom due to transient force at the second degree of freedom, plus I can then find the response due to transient force at the nth degree of freedom. HIN convolution with F and T, right. And since I can determine the response of any given forces at any degree of freedom using the impulse response functions also form in their own right a model of the system, right. And that is why this also characterizes the system and is referred as the model in the time domain, the response model in the time domain. FRFs constitute the response model in the frequency domain. So, I think now we can stop here and we will continue in the next class. Thank you.